Welcome to this exploration of transformative frontier in technology, AI for science. We are currently witnessing a unique intersection where machine learning and natural sciences converge to solve some of the world's most pressing challenges. That diagram on the right, a wave function feeding into a neural network, is a hint about where we are going. What you're looking at is the core idea of this talk distilled into a single image: physics on the left, machine learning on the right, and a bridge between them that is changing what science can actually do. For centuries, science has relied on human mind to formulate hypotheses and manual experimentation to test them. Then came the digital revolution in the 1960s, allowing us to use computers to solve complex equations, though often at a very high computational cost. Today, we are at the early dawn of an AI revolution that is impacting every aspect of this process. AI is now helping scientists interpret massive experimental datasets uh, that drive automated laboratories and even navigate millions of research papers that no human could possibly read alone. But perhaps the most important and exciting development is the creation of third pathway for the discovery, the AI emulator. Through this presentation, we will see how these emulators allow us to use the fundamental laws of physics to accelerate discovery at a pace previously thought impossible. This journey begins with a simple yet extraordinary fact: a world is described by mathematics. Part 1: The problem. Exact equations, impossible costs. Physics gives us perfect equations, but the computational cost of solving them grows beyond reach. One of the most profound realizations in the history of science is that the physical world follows simple mathematical laws. Equations that can be written on a single piece of paper allow us to predict the future with staggering accuracy. Take, for example, the electron. By using theoretical physics, we can calculate its magnetic strength to 13 significant figures. When we conduct an experiment to measure that same value, the results agree perfectly within those tiny error bars. This level of precision tells us that we have the source code for the universe. Whether we're looking at the Earth's atmosphere, new materials, or life-saving drugs, we have the equations that describe them precisely. So, why haven't we already designed every drug and material we need on a computer? The answer lies in a frustrating irony first noted by physicist Paul Dirac. Nearly 100 years ago, while the laws are simple to write down, the equations they produce are much too complicated to solve. For a century, we have been stuck in a situation where we know the rules of the game but can't calculate the outcome for anything complex. A molecule as simple as caffeine remains out of reach for direct mathematical solution because the computational costs grow exponentially with every electron you add. This bottleneck is exactly where the AI emulators are designed to break. The dimension explosion of Schrödinger's equation. In one dimension, if you want to represent a quantum wave function on a grid, you need 1,000 grid points. Okay, 1,000 numbers. Your laptop handles that for breakfast. Now go to 3 dimensions, the real world we live in, for a single particle. The 1,000 points per dimension becomes 1 billion grid points. That's already getting uncomfortable, but it's still manageable with modern hardware. Now let's try something real. Let's try to calculate the exact quantum wave function of caffeine, a molecule so simple that right now many of you are metabolizing it. Caffeine has 24 atoms, around 1 or 2 electrons, and here's where the explosion happens. The Schrödinger's equation for many electron system doesn't live in 3 dimensions. It lives in 3n dimensions, where n is the number of electrons. For caffeine, that's a 300-dimensional space, and if you put even just a modest grid of 10 points along each dimension, your grid has 10 to the power of 300 points. 10 to the 300. There are roughly 10 to the 80 atoms in the observable universe. The number of grid points needed to represent the caffeine wave function is not just larger than the number of atoms. It's incomprehensibly cosmically larger. This is not a problem we solve by buying a bigger computer. This is what mathematicians call the curse of dimensionality, that it's a single deepest reason why computational chemistry has been limited for a century. The question on the table is there a way out? Part 2, the three oracles of scientific discovery: experiment, simulator, emulator, each with its own trade-off in speed, cost, and scalability. To understand the role of AI, we must look at how the scientific method has evolved through what we call the oracles, source of truth that inform our discovery loop. For most history, the only oracle was experiment. A scientist would form a hypothesis, test it in the lab, and use the observations to refine the ideas. This iterative loop is the foundation of science, but it is slow and expensive. In the 1960s, a second oracle emerged: simulation. Because we knew the underlying equations were accurate, we could use digital computers to solve them directly rather than doing a physical experiment. This was revolutionary, but simulation has a major drawback. It's computationally intensive and slow. Now we're introducing the AI emulator as a third oracle. An emulator doesn't replace the first two, it complements them. It learns the patterns of physical laws and can predict the results of a simulation or experiment thousands times faster. By combining the traditional scientific method with agentic AI and deep learning emulators, we can now search the vast space of molecules and materials at a scale that was previously unimaginable. I mean, that's seriously GTP4, Cloud, Gemini, these are extraordinarily powerful models. They absorb more text than any human will ever read. Why can't we just feed them chemistry papers and ask them to predict molecular properties? The answer is in this slide, and it comes down to something called no free lunch theorem. In machine learning, this theorem says that there's no single model that's best at all tasks. Every model reflects the assumptions baked into the architecture, and those assumptions had better match your problem. You cannot learn purely from data without making some assumptions, known as inductive bias or priors. In the world of large language models, the inductive bias is very light. We use massive amounts of data and let the model figure out the patterns through mechanisms like attention. However, in science, data is scarce and expensive. It can take a PhD student an entire year to determine the structure of a single protein. Fortunately, science gives us something LLMs lack: a very rich inductive bias in the form of physical laws like Schrodinger's equation. We also have conservation laws: mass, energy, and momentum are always conserved, and symmetries like invariance and equivariance, where physical properties shouldn't change just because you rotate a molecule in space. The challenge is how to use this knowledge. A famous blog by Rich Sutton called The Bitter Lesson warns that researchers who bake in too much human knowledge often lose out to those who simply use more compute and data. The AI emulator provides the solution to this dilemma. Instead of ignoring our beautiful equations or trying to manually hardcode them into every network, we use the equations to generate our own data. This allows us to scale with compute while still respecting the fundamental laws of physics. Part 3, the emulator pipeline: from simulator to massive synthetic data, and then from synthetic data, a deep learning emulator that replaces iteration with single forward pass. Let's look under the hood of how an AI emulator is actually built. The process begins with a simulator, traditional software that solves differential equations directly. This simulator is accurate but slow. We use it to solve the equations for thousands of different scenarios, which generate a high-quality synthetic dataset. Because this data is generated by a computer, it's perfectly labeled. We do not need humans to manually identify parts of the data. We also have an unlimited supply of it. As long as we have compute, we can keep generating more. We then use this synthetic data to train a neural network, which becomes our deep learning emulator. The magic happens once the training is complete. While the original simulator had to go through a slow iterative numerical process, the emulator is a feed-forward network. It's just a mathematical function that can be calculated almost instantly. We amortize the high cost of initial data generation over thousands or millions of times. We will use the emulator in the future. On average, these emulators are 3 orders of magnitude faster than the simulators they replace. This means a process that once took days can now be completed in a fraction of a second, fundamentally changing the pace of research. Now let's go a little bit more in detail on this slide. When we start with the step one, that is the simulator you see on the left. This is the structure step. You use traditional physics solvers, expensive, expert built, encoding all the known physical laws to generate your data set. This is slow, it costs real money, but you only do it once. Step two, massive synthetic data. The simulator produces perfectly labeled data at a scale no wet lab could match. Not thousands of data points, millions. Every input-output pair is exact. The labels are grounded on truth in physics. Step 3, the emulator. Now you bring in scale. You train a large neural network designed with the right architectural symmetries on the data. The network learns to mimic the simulator's output without running the simulator's math. The result, a model that executes in milliseconds, thousands of times faster at near zero marginal cost. Structure generated the data, scale learned the pattern. Let me walk the fundamental trilemma of discovery. Let me walk the triangle. In the top left, traditional quantum chemistry methods such as CCSDT, the gold standard, extremely accurate, extraordinarily slow, essentially zero generality. You can only apply them to systems you can afford to compute. That is the top vertex. At the bottom right, classical molecular dynamics, very fast, highly general, but accuracy? You're given so much physics that for anything involving electron behavior, the model simply can't be trusted. That is the speed generality corner. And there and here in the middle is where the emulators live, not at any vertex, at the intersection of all three. Now I want to be very careful here. Emulators don't beat physics. They don't get the CCSDT accuracy on every system. What they do is dramatically shift the Pareto frontier. They push towards the center of the triangle in a way that the brute force methods cannot. And as the training data grows, as architecture improves, as more physics gets encoded into the network design, the emulator target moves closer and closer to that top accuracy vertex. It's not there yet, but the trajectory is clear. The question is not whether the emulators will dominate computational science. They definitely will. The question is how fast. Scaling reality, the Earth system. I want to make this real for a moment. Weather prediction, not climate modeling, actual day-by-day weather forecasting. Right now, today, the best weather forecasts in the world are produced by running the Navier-Stokes equations, the fundamental equations of fluid dynamics on some of the most powerful supercomputers ever built. The European Center for Medium Range Weather Forecast, the ECMWF, runs a machine that performs something like quadrillion calculations per second. And even at that scale, producing a 10-day global forecast takes hours of continuous computation. Here is the challenge from this slide, and I want to appreciate how audacious it is. Complete UK 8-day weather forecast. Time allowed is just 1 minute. Compute available a single A100 GPU, a single GPU, 1 minute. This is not a thought experiment. This is what Google's GraphCast and Huawei's Pangu Weather have actually achieved. And in some meteorological benchmarks, they have matched or surpassed the ECMWF at a fraction of the cost. How? The slide tells you. You train a foundational model, a large neural network on decades of public simulation data. The ECMWF has been running its model since the 1970s. That's the 50 plus years of high quality simulation outputs, millions of simulated atmospheric states. You use that corpus as training data. The neural network learns the Earth atmosphere dynamics, not by solving equations, but by learning the statistical structure of what those equations produce. The iterative physics engine is replaced, not because physics is wrong, but because the neural network has internalized it. Part 4, Domain Breakthroughs. From material design to protein folding, emulators are rewriting what's computationally feasible. Mesoscale designing stable materials in a vast universe. Materials discovery in the traditional sense looks like this. You have some intuition or some prior art and you pick a candidate. You synthesize it, you characterize it, you find out it's unstable or the wrong color or the wrong conductor, and then you go back and try again. This is a random walk through chemical space that has produced everything from aspirin to semiconductors, but it is achingly slow. Now, look at the MetaGen emulator architecture on this slide. It's built on conditional diffusion. It's exactly the same mathematical framework that powers image generation models like DAL-E. But instead of denoising images, it denoises crystal structures. You start with noise, a random arrangement of atoms. You condition on what you want, a stable material with these electronic properties, this symmetry group, this target band gap, and you iteratively denoise towards a crystal structure that satisfies your conditions. What comes out is not a randomly sampled crystal. It's an intelligently targeted candidate, pre-filtered through the learned physics of stability and property satisfaction. The emulator acts as a lens, compressing your search from 10 to the 60 candidates to a tractable shortlist. This is hyper-fast downstream screening. The wet lab still validates, but the search space just collapsed by orders of magnitude. The dimensionality cheat code, density functional theory. In 1965, Walter Cohn proved something remarkable, and it earned him the Nobel Prize in Chemistry in 1998. He showed that you don't need the full quantum wave function to calculate the physical properties of a many electron system. The wave function lives in 3n dimensions, as we established earlier. That's 300 dimensions for a caffeine molecule. But Cohn proved that all the information you actually need is contained in the electron density, a function of just 3 spatial dimensions. The object, the wave function, is impossibly complex. Scales exponentially can't compute. The shadow. The electron density contains all the necessary properties, scales cubically at worst, and it's computable. This is what is called the Hohenberg-Cohen theorem, and is the foundation of density functional theory, or DFT, a mathematical theorem that tells you that you can use a simpler equation instead. DFT is so powerful that it currently accounts for a third of all global supercomputing workloads. Every time a researcher runs a drug discovery calculation, a material science simulation, a battery design study, there's a good chance that DFT is doing all the heavy lifting. And then there's a catch. DFT has a problem. It requires what's called the exchange correlation functional, a term that captures quantum interactions between electrons. And this functional is strictly speaking unknown. For 60 years, scientists have crafted over 800 hand-tuned approximations. The matrix of functionals. This scatter plot tells you everything you need to know about the current state of quantum chemistry approximation. On the x-axis, chemical accuracy threshold, the level of accuracy required for calculation to be trusted for, say, a drug design or materials prediction. On the y-axis, error, lower is better. On the right side of the x-axis, computational cost. Moving right means spending more. Up here in the upper right, human approximations, high error, high cost. This is legacy. 60 years of brilliant chemists handcrafting functionals, and the best they have achieved still sits above the chemical accuracy line for many systems. Down here, the Scala AI emulator, lower error, lower cost, below the chemical accuracy threshold. Scala is what happens when you replace handcrafted approximation with learned ones. Instead of a physicist writing down an analytical form for the exchange correlation function, a neural network learns the function directly from labeled quantum chemistry data. The architecture matters enormously here. Scala uses message passing neural networks, the same class of architecture used in graph neural networks, where atoms pass information to their neighbors and then neighbors pass information back, in a way that respects the physical structure of a molecule. The geometry of the graph encodes the geometry of the chemistry. The result, a model that learns not just one functional for one class of molecules, but a general functional that achieves chemical accuracy across many systems at a fraction of the computational cost. This is not incremental improvement. This is the kind of result that in 10 years will be a turning point. The biological scale, the curse of sequentiality. Can we push these emulators all the way to biology? Biology is essentially complex chemistry, where the sequence of DNA leads to the structure of proteins, and that structure determines their function. But protein function isn't static, it's about dynamics, how they wiggle, jiggle, and fold. To simulate this, we use molecular dynamics, solving Newton's laws of motion step by step. Here we hit the curse of sequentiality. Atoms vibrate at a femtosecond scale, but interesting things like protein folding happen over milliseconds. This requires a staggering 10 to the power of 15 sequential steps. Because this process is sequential, we can't just throw more parallel GPUs at it to make it faster. The solution is to use emulators to group atoms into chunks and predict the forces between them. This hierarchical process allows us to run simulations for proteins with up to 10,000 atoms, a massive leap from the previous limits. We can even use AI to sample directly from proteins' equilibrium distribution, effectively skipping the long sequential timeline of the simulation. This work was recently featured on the cover of Science, proving that emulators can bridge the gap from subatomic world to the machinery of life. Emulating biomolecular dynamics. Here's what traditional molecular dynamics looks like for a protein. Step 1. You start with an initial configuration, the protein in some arbitrary unfolded state. Step 2. You compute the forces on every atom from every other atom. Step 3. You move each atom according to Newton's second law. Step 4. Repeat for 10 to 15 steps. The computational cost of this is staggering, and even with the fastest supercomputers and the most aggressive parallelization, we can reach microseconds of the biological time at best. However, the folding, which happens at the millisecond scale, is largely out of reach. Now look at what the biomolecular emulator does. Instead of simulating the trajectory step by excruciating step, it directly learns the equilibrium distribution of protein conformations. Think about what that means. The simulator asks, what happens next? The emulator asks, what is the probability of each possible state? It jumps from question to question, from trajectory to distribution. The biomolecular emulator is a conditional diffusion model for molecular conformations. It starts with the noise, a random arrangement of backbone atoms, and denoises towards structures that are thermodynamically plausible. It can generate, in seconds, thousands of diverse, physically realistic protein conformations that represents the equilibrium ensemble. Why does this matter? Because a protein's function, its ability to bind a drug, catalyze a reaction, trigger a signaling cascade, depends not on one static structure, but on its ensemble of conformations. The emulator captures the ensemble directly. Synthesis, the bypassing of iteration. Let's bring it home. Look at the diagram in front of you. 4 domains, one central concept. Weather systems, metagen crystals, Scala electrons, biomolecular proteins, different scales, different physics, different computational curses. The one common structure at the center in the blue, the feed-forward jump. Here is the historical bottleneck stated. Whether forecasting global atmospheres or folding 10,000 atom proteins, the historical bottleneck across all scales of science has always been the same: sequential iterative simulation. Sequential iterative simulation. Each word is a load bearing. Sequential because time has to pass, step follow step. You cannot skip ahead. Iterative because the equations have no closed form solution. You must run many cycles to converge. Simulation because you're not computing, not measuring. The combination is what's expensive, the combination is what's slow, and for a century it was the only option. Deep learning emulators collapse millions of sequential time step calculations into a single direct feed forward jump. We are no longer limited to simulating reality frame by frame. We can compute the blueprint directly. Compute the blueprint directly, that's the phrase, and it's the name of this entire lecture. It means skip the simulation, go from inputs to the final answer in one pass, not by ignoring the physics, but by having learned the physics so thoroughly that iteration is no longer needed. This is the paradigm shift. This is what emulation means, not a better simulator, a replacement for simulation itself. This is where the computational science is heading towards. Thank you for being with me on this journey of this presentation.